Hello and welcome to the presentation of our research paper, Measuring Human Perception of Airflow for Natural Motion Simulation in Virtual Reality. I'm Cai from Zhejiang University, and I will be presenting on behalf of my co-authors. And as many of you know, one of the leading theories for motion sickness in VR is the sensory complex theory, which suggests that motion sickness arises from conflicts between visual motion perception and non-visual sensory systems. This highlights the importance of aligning the visual sensation of self-motion, which is visual vection, with non-visual sensation of self-motion, which is defined as bodily vection in the study, to reduce motion sickness. Please note that in this study, we adopt a broader definition of vection, referring to any sensory stimulus that induces a self-motion perception, distinguishing between visual and bodily vection. Guided by this idea, many studies have explored various multimodal stimuli, such as auditory flow and vibrations and airflow, to alleviate a sensory conflict. These studies use different wind sources and wind speeds to simulate virtual motion, reduce motion sickness, and enhance presence. And however, there is a significant gap. Most studies rely on simple airflow designs, like constant headwinds or equating airflow speed directly with virtual speed. Additionally, the varied designs of wind sources and virtual motion scenarios also make comparisons challenging. As a result, there has been limited exploration of quantitative relationship between virtual motion and corresponding airflow stimuli for subjective consistency. So our study hypothesizes that subjective consistency between visual and bodily vection is essential for reducing motion sickness and creating a natural motion experience. We made the following contributions through 3 experiments. Firstly, the first experiment identified the subjective mapping relationship between virtual speed Vs and airflow speed As for linear motion in VR, showing a linear relationship. The second experiment introduces the concept of airflow gradient to simulate curvilinear motion, revealing a relationship between angular velocity omega, radius r, and airflow differential delta As. Similar to centripetal acceleration. And the third experiment proposed a dynamic airflow scheme that integrates these relationships to simulate complex motion and validated its effectiveness. Our experiment used an airflow array consisted of 9 fans and a 24-centimeter wind tunnel. Each fan is individually controlled via PWM signals, producing uniform airflow ranging from 0 to 4.5 meters per second. To enhance airflow contact with user's face, we use simulated airflow noise to balance the wind sound across different experimental conditions, instead of using noise-canceling headphones. The experiment included 3 virtual scenarios for linear motion, circular motion, and complex street motion in VR. All motions were passive movements along fixed path, with no active control needed from participants. Our first experiment aimed to measure the subjective mapping relationship between the virtual speed of visual motion and the airflow speed of airflow stimuli during constant linear motion in VR. And this experiment used a cross-modal matching task and the method of adjustments from psychophysics. We presented both virtual and airflow stimuli simultaneously to the participants in VR. The virtual motion was a fixed constant speed linear motion with 11 Vs levels ranging from 1 to 46 meters per second. The airflow was uniformly distributed with an initially random airflow speed. And participants adjusted the AS using controllers until they feel that the bodily vection caused by the airflow matched with the virtual motion. After maintaining the match for 4 seconds, they reported their real-time motion sickness level using the FMS. This experiment involved 15 participants, each experiencing 16 instances of virtual motion in the VR environment. And of these, 55 were cross-modal matching tasks with 11 VS levels, each repeated 5 times, and also 11 trials of virtual motion without airflow. Each motion cycle was followed by a 10-second rest period. This provided with 825 points to fit the relationship between VS and AS. The results were clear. A strong linear relationship exists between AS and VS, with an R-square of 0.579 for all samples and 0.994 for group averages. The fitted function was AS equals 0.055 multiplies VS plus 0.171. This indicates that when aiming for subjective consistency, airflow can simulate virtual motion that is much faster than its own speed without needing to match the virtual motion speed directly. This might be because proprioception suppresses skin sensations during physical walking, making it harder to feel airflow. However, in VR, where proprioception is almost absent, people are more sensitive to airflow. The linear relationship is common in cross-modal matching and provides an excellent foundation for simulating more complex virtual motions. And next, we conducted the second experiment to measure the subjective mapping relationship between angular velocity and radius of the virtual motion and the left-right speed difference, which is delta AS of the airflow stimuli under constant circular motion in VR. Since few studies have explored the airflow metaphors suitable for simulating curvilinear motion, we introduced the concept of airflow gradient. This model simulates curvilinear motion with unevenly distributed airflow. The central airflow speed is set to match the virtual speed, as determined in experiment 1, with the airflow on both sides adjusted by a variable amount, delta AS. When the virtual motion turns left, the airflow on the right side is stronger than on the left. And the design of the airflow metaphor is based on the concept that when turning, the side further from the curve center moves slightly faster and should have faster airflow, while the motion direction is always facing forward. This experiment also used a cross-modal matching task with a virtual motion set to constant circular motion with 5 levels of angular velocity omega, ranging from 25 degrees per second to 45 degrees per second, and 8 levels of radius, from 2 meters to 37 meters. Omega was then between subjects variable and R was then within subject variable. Participants adjusted delta AS to match visual action, while the AS was kept fixed. We recruited 40 participants divided into 5 omega conditions. Each participant completed 48 trials of virtual motion, 40 cross-modal matching tasks with 8 R levels, each repeated 5 times, and 8 trials without airflow. This provided 1,600 data points to fix the relationship between delta AS, R, and omega. And given the increased complexity, we first analyzed the data with ANOVA and Pearson correlation to examine the relationship between omega, R, and delta AS. Results show that both omega and R significantly affects delta AS with an interaction between the two. And the effect of R on delta AS seems linear, while omega didn't show a similar relationship. So we then performed regression analysis, which revealed clear results. For each omega level, the relationship between R and delta AS was linear, with R square values for group means above 0.975. Based on these findings, we modeled the relationship between omega, R, and delta AS, and after testing several possible models, we got the final fitted model, which is structurally similar to the centripetal acceleration formula, A equals omega squared multiplied by R, and provides a good fit with an R squared of 0.918 for group means. This result is surprisingly consistent with physical intuition. We did not select more complex quadratic, cubic, or power function models due to overfitting concerns. After learning how to use airflow to simulate linear and curvilinear motion, we propose a dynamic airflow scheme, DA, that integrates the findings from our previous experiments. We compare this scheme with the constant airflow, CA, and no airflow, NA conditions normally used in previous studies to assess how the subjective matching between airflow and virtual motion affects motion sickness, presence, and vection consistency. The experiment was conducted in a complex virtual motion environment consisting of 19 segments with different straights and curved roadways. And participants experienced passive motion with natural speed changes averaging about 10 meters per second. 15 participants were asked to experience 5 minutes of virtual motion under each of the 3 conditions. And during the motion, they focused on consistency between bodily and visual action and pressed the controller when they felt a mismatch. And for every 15 seconds, they reported their motion sickness level using the FMS, and after each condition, they completed questionnaires to assess motion sickness presence and vection consistency. The results were clear. SSQ scores show that DA caused significantly less motion sickness, and FMS trains indicate less real-time motion sickness accumulation. In most straight and curved segments, users in the DA condition reported the shortest mismatch duration between bodily and visual vection, and later reported significantly higher vection consistency and presence. And overall, our work provides reliable quantitative guidelines for future airflow-based motion simulation methods. However, there are a few key points worth discussing. Firstly, while the relationship between delta AS and R omega appears to align with physical intuition, it also shows that the airflow virtual motion relationship is not a direct physical correlation. If it were, delta AS would be independent of R, as in real-world curvilinear motion. And so it tells us that curvilinear motion in VR may create a visual perception of lateral motion that lacks the physical cues from real-world forces. And the effectiveness of the airflow gradient metaphor may stem from its ability to provide the physical cue related to centripetal acceleration in magnitude, and which compensates for the absence of lateral motion cues. Our study strongly opposes the crude design that equals AS directly with VS, as it results in airflow intensities far beyond what is needed for subjective consistency. This may lead to airflow being perceived as resistance rather than a motion cue. Additionally, our experiment revealed important connections between vection consistency and motion sickness. Consistency between bodily and visual vection is negatively correlated to motion sickness. However, the effect of dynamic airflow on vection consistency is greater than its effect on motion sickness, which suggests that vection consistency plays a key role in alleviating motion sickness beyond just the refreshing effect of airflow, but it's not enough to eliminate it, as other factors such as rapid eye movement, rendering delays, and passive motion still contribute. Our study also has some limitations. Due to the technical limitations of conventional wind sources, we couldn't implement an AS equals VS control group with an average wind speed over 10 meters per second, and there was an airflow delay at transition points during complex motion. Also, due to participants' sensitivity and tolerance, we pre-screened participants and limited the intensity range of virtual motion in the experiments. And moreover, if the airflow gradient ability to simulate curvilinear motion really stems from its representation of lateral motion, there could be better airflow metaphors for simulating such motions. And finally, while the proposed airflow virtual motion mapping relationship is reliable in structure, the specific parameters may need adjustments for different VR environments and tasks. And that concludes my presentation. Thank you for your attention, and see you in France.